Hello and welcome to Calc Chat 16. This is Graph Analysis Part 3 and this is the final part of our graph analysis series. Today we're going to talk more about graph analysis and specifically we're going to talk about how to use the second derivative to find more information about our graph. So when we found the first derivative and we used a sign chart, that helped us find the intervals of increasing and decreasing, and that also helped us find our maximums and minimums. And so we had our critical points and we found where our derivative was equal to 0. Once we had those critical points, we looked on values on either side and we determined if the derivative was positive or negative. And then we determined if that was increasing, decreasing, and then based on that, we said it was a local max or min. Our second derivative is going to help us with concavity, which we're going to talk about in a second, and it's going to talk. We're going to talk about maximums, how to find the maximum and minimums from the concavity. So first things first, we have to discover what is concavity, what is concave up, what is concave down. So concave up, I was always told, is like a cup. So if I have a parabola, this parabola is concave up. I can hold water in that parabola. And concave down is like a frown. Easiest example, this parabola, if I drew a 2 eyes right there, that would be a frowny face. It would obviously be very, very sad. And so these are probably the easiest examples of visible concavity. We're going to be dealing with examples like cubic functions that have very slight concavities. And if I notice, from this point, let's call that -2 to about 2, I do have a concave down. If I drew 2 eyes right there, that would be a frowny face. And then from about 2 on, I could hold a little bit of water. It wouldn't be that much, but this would be concave up. So right here is concave down, and over here is concave up. So we're going to be dealing with functions that are quadratics, cubics, quartics, quintics, and so forth. So our concavity might not look as drastic as a parabola, but it is still there. Another thing to note is that linear functions do not have concavity. If I think about the function y equals x, y prime is 1, y double prime is 0. It has no concavity. So in order to find concavity, we need to be able to take the second derivative. So if I can take the second derivative, if my function is twice differentiable, then if the second derivative is positive, it is concave up, like a cup. If my second derivative is negative, it's concave down, like a frown. And I have to always think of this as like money. So if I have more money, I'm happy. If I have less money, I'm sad. So in the first derivative, we talked about critical points. In the second derivative, we talk about points of inflection. And so that's where our concavity changes. So going back to the example I said of kind of like the cubic function, how it just slightly shifts from concave down to concave up, our point of inflection would be about there. So on this side of the function, I'm concave down. On the other side, I'm concave up. That's our point of inflection where concavity changes. So let's just jump into a problem. So given this function, we're looking for the concave, where it's concave up, concave down, and the local maximum and minimums. And so let's first focus on concave up and concave down. So in order to do that, I need to first find the first derivative. So 12x squared minus 24x, and then my second derivative, 24x minus 24. And so I need to find my points of inflection, so I need to find where my second derivative is equal to 0. And so if I take out a 24, I get x minus 1 equals 0. And then if I take out, if I divide both sides by 24, I get x minus 1 equals 0, so I get x equals 1. So x equals 1 is my point of inflection. All right. So going from there, we make a sign chart, just like we did with our first derivative. So 1 is in the middle, 0 is less than 1, 2 is greater than 1. So I just picked points on either side. So I'm going to plug them back into second derivative. If you want to plug it into the original, you can, but I like focusing on the simplified function because that just makes it so much easier. So I'm going to plug in 0 for x, and when I plug in 0, I get 0 minus 1. That is a negative number, so my concavity is negative. This is concave down. When I plug in 2, I get 2 minus 1, I get positive. So this means my concavity is concave up. Remember, more money, smiles, less money, sad. So I found my intervals of concavity, and if I sketch a function, I can kind of see, okay, so here's my point of inflection at 1. So this is where my function is changing. From negative infinity all the way to 1, I'm this concave down function. Then all of a sudden at 1, I switch, and now I'm concave up. So our point of inflection could be, let's say, right there. So I switch from being a frowny face to being a cup. So this gives us a really good idea of where our local mins and maxes are, because I know that if my function is concave down, this has to be a local max. And if my function is concave up, this has to be a local min. I can't have a function with a concave up that we're going to say that's the max unless the interval is just at that point. So I know anytime I have a concave up, it's got to be a minimum. So first, let's write down our intervals of concavity. So our intervals of concavity are from negative infinity to 1, concave down, and then from 1 to infinity, concave. So what I need to do now in order to find the minimums and maximums is I need to go back to first derivative. So to find local mins and maxes, go back to first derivative. But this process is going to be a lot shorter. Once I have my concavity, I know that my max has to be somewhere in here, and my min has to be somewhere in here. So whatever critical values I find, if that critical value is greater than 1, it's a min. If it's less than 1, it's a max. So my first derivative was 12x squared minus 24x. So f prime equals 12x squared minus 24x. I'm going to set that equal to 0. And then I can pull out a 12x, left with x minus 2. 12x equals 0, x minus 2 equals 0, x equals 0, x equals 2. And so these are actually the points I put on my sign chart. But I know this is a, what did we say? We said this was a local max because that's where it was concave down. So this is a local max, local minimum. So once we find the second derivative, it's a little bit easier to go back. All I need to do is look at my critical points, and then I can tell immediately where my local max and local min are. So this was using the second derivative. Again, all it really helps us with is concavity and maximum and minimums, but we're going to combine it with our first derivative test to find as much information about our function as possible. So please come to class with any questions that you may have. Thank you for watching this video, and please be sure to like and subscribe.